Okay, so hello everybody. Welcome back to the GBO Science Lunch Talk series. Today, I have the pleasure of introducing Mark Siebert, who is a third-year graduate student at the University of Virginia. And he'll be talking about his work with the GOTHAM survey, the Green Bank Telescope observations of TMC1 hunting for aromatic molecules. A beautiful acronym, if ever I've heard one. And he'll be telling us a bit about his Scrabble winning work with methyl carbon chains working with TMC1. So when you're ready, Mark, take it away.
Awesome. Thank you, Jesse, for the introduction. And thanks for everyone who came out during their lunch hour to hear about some of the recent work I've been doing. Like you said, I'm going to be talking about some of the recent stuff I've been doing as part of the GOTHAM collaboration concerning carbon chain chemistry in TMC1. And to give a little bit of background on what I'll be talking about, when we talk about cold carbon-rich chemistry in the interstellar medium, the torus molecular cloud has always been one of, if not the prime example of this kind of chemistry. It's been studied for over 40 years by radio astronomers, and it's well known for its very bright rotational emission lines from many different kinds of molecules in this source. And it's really one of just a handful of sources that have really paved the way for the field of astrochemistry as a whole, and have really pushed the bounds of what we know and what kinds of molecules we know can form in interstellar space. And it's still studied to this day. And so it's a prestellar cold core, while TMC1 is a core inside the complex with a temperature of about 11 Kelvin. So it's very cold, very dark. And because it's so cold, it has consequently very narrow line widths. And in recent years of studying TMC1, and of particular interest to the GOTHAM collaboration, cyclic molecules have been of very scrutinized and of main interest in this source, with the detections of things like benzonitrile and PAH molecules. But I'm actually going to take it back to some of the original molecules that were studied in this source, and those are related to the linear carbon chains. So some of the brightest lines that you'll see in TMC1 are from the cyanopolyene family. So it's HCXN, where X is an odd number, and HC3N is one of these linear chains shown here. And then there are other variations on these, like acetylene sort of chains. And the main component that you have here is a long carbon chain that's unsaturated with these alternating triple and single bonds. And what makes it a cyanopolyene is when it's terminated in a nitrogen, and that's what makes it so bright, because it gives it such a big dipole moment. But what I'm going to be talking about today is just a slight variation on these chains. And there are some other variations, including O-terminated and sulfur-terminated chains. But I'm going to talk about if we took one of these hydrogens and replaced it with a methyl group. And so it's no longer technically a linear molecule, although it's very linear. This is what we call a symmetric top molecule. And these are split into two families based on whether they're terminated in a nitrogen or a hydrogen. And so the former, so shown here, are the methyl cyanopolyenes, and the latter are the methyl polyenes. And these have been studied in TMC1 for about 3 decades now, since the detection of CH3C3N. And they are very related to the linear carbon chains in their chemistry, and they've been detected up to lengths of about 6 carbons in that carbon chain backbone, whereas the more abundant linear species have now been detected up to things like HC9N and HC11N. So they're not as abundant, and they're harder to find those long ones. But also, we don't really know a whole lot about how these chains are built up in the source. We have ideas, but since they've been studied in all different kinds of surveys, it's really not been constrained very well how these things are forming and how they interact with all the other species in TMC1. And another really important part about these carbon chains lies in their excitation physics. So all symmetric tops, or all the carbon methyl carbon chains have what we call C3b symmetry, which means that the rotational energy state is defined by the total angular quantum number J, as well as the projection of that onto the unique axis of rotation. So kind of along the that long carbon chain is the unique axis. And so you can have K states between 0, which corresponds to this molecule spinning kind of head over heel, to a K state where it is equal to the total quantum number, where it's just spinning along that, that axis. And something really interesting arises due to the nuclear spin statistics on the hydrogens in that methyl group, where if you have a K value equal to 0 or a multiple of 3, the species is in what we call asymmetry, whereas if it's equal to anything else, the molecule is in an E state. And what's really important about these two states is that it's very, very hard to interconvert between the two. So once a molecule is in a K equals 0 state, it's going to be very hard for it to get into something like a K equals 1 or a K equals 2 state. And that's really useful for probing the formation conditions, as well as different cooling mechanisms in whatever source you're looking at, because you kind of have an imprint of the conditions when this molecule was formed. So this was done in 1993 for methyl cyanide, where they showed that the A to E ratio has equilibrated to the rotational temperature in TMC1, which is indicative that this molecule formed at these low temperatures and is still consistent with that. But that's not seen for all molecules, and it also hasn't been done for the longer chains. So we'd like to do that as well. So with all of this, we see that these families of molecules are really important to constraining both physical and chemical processes in the interstellar medium, but there still is a lot that we don't know about them in TMC1. And we've also never had a single batch study of all these chains, and that's precisely what we want to do. And that is actually where the GOTHAM collaboration comes in. So as Jesse said, GOTHAM stands for GBT Observations of TMC1, Hunting Aromatic Molecules, and we have this wonderful logo. This is a large program that started on the Green Bank Telescope back in 2018. And this is just a very rigorous spectral scan of the Taurus molecular cloud, the cyanopolylene peak, that covers X band currently, the KFPA, as well as Ka bands. This is up to date for the second data release of GOTHAM, which is what was used to do this work. And this survey has near continuous frequency coverage in these bands, and very low noise level from the amount of hours that we put in on this source. And one of the most defining qualities of GOTHAM is our extremely fine velocity resolution. And like I said on the first slide, because molecules are so cold in TMC1, their line widths are very, very narrow. But there's actually a lot of structure beneath those lines if you have the sensitivity to have a lot of channels on that line. And there's actually many velocity components below that that you can use to study the different physics and relative populations of these molecules in TMC1. And GOTHAM is letting us do just that. And so far, and I'm just going to highlight 2 results in the past year. There have been many, many more. But in the past year, we've had the discovery of a new isocyanide by Shui et al. 2020. I think CC might be giving a lunch talk on this later this year, so stay tuned for that. And of course, one discovery we're extremely excited about is the first ever detection of significant emission from individual PAH molecules. So these are nitrogen, these are 1 and 2 cyanonaphthalene, which are just basically 2 benzene rings stuck together with a CN group attached to it that gives it a nice dipole moment that we can detect. And this was a very, very exciting discovery. So the power of the GOTHAM survey is really there. And not only does it present the sensitivity to search for new interstellar methyl carbon chains, but it also has the bandwidth and the resolution to perform a brand new self-consistent study of all of the previously discovered ones as well. And this is really important to constraining both chemistry and physics in this source. So this is exactly what we want to do with the second data release of GOTHAM. And here's how we're going to do it. So we have this wonderful data set, and we now need to come up with a reliable and consistent method to study all the species we're after. And namely, the species that we want to study are three species in the methylcyanopolyene family and 3 species in the methylpolyene family. Now, these 4 on the top here have been discovered in TMC1 and have been characterized before, but we want to do them again for consistency's sake. And we also want to look for the next longest species in each family, which should be the next brightest in these. So we have 6 molecules we're looking for, but also don't forget that we want to study their A and E symmetry states separately. We can almost treat them as separate molecules because it's so hard to convert between the two. So because we want to treat them separately, that's almost like we're doing a whole 6 more molecules on top of these 6. So in total, we have 12 species that we want to fit, and they have varying numbers of transitions in our frequency coverage and many different parameters governing how they appear in our data. And to explore all of this information at once, we've adopted a Bayesian approach using this Markov chain Monte Carlo fitting routine. And this routine is kind of predicated on a few key assumptions. The first is that whatever molecule we're searching for is in fact present in TMC1. And that's just to say that it has some characteristic column density and some characteristic excitation temperature, as well as some other parameters like line widths and line positions. Another assumption we have to make is that the spectroscopic constants of whatever molecule we're looking at, or whatever symmetry state we're looking at, are known beforehand. And these molecules have all been studied in the lab and have fairly well constrained rotational constants. A third assumption we have to make is that the noise is well characterized by an RMS, and that is not some red noise or weird frequency dependent things going on. This is very important for this routine to get a good fit on these molecules. And lastly, we need to assume, based on prior information, we make the assumption that there are 4 velocity components that contribute to emission for any given molecule. And that is kind of going back to what I was talking about, how since we have this spectral resolution, we need to account for all these different components. So with all this information, this MCMC approach explores a 14-dimensional parameter space. And it samples that parameter space using priors from other linear molecules. And given these assumptions, it converges and finds a set of parameters that are consistent with the data. And this is from Ryan Loomis's paper on HC11N from earlier this year, where this method was applied to find this molecule. And this is a corner plot displaying the results of the MCMC fit. So on the diagonal, we see the posterior distributions, which are basically probability distributions for your many different parameters that you're fitting. And in the cells, we see the covariances between the parameters. So you can see which variables are highly covariant with each other. So things like column density and source size are going to really depend on each other to derive, you need one to derive the other. That's why they're shaped like this. But things like rest velocity and column density are not very covariant. So they appear more as just Gaussian blobs on here. So yes, this is a very powerful routine. And just from fitting the data, these distributions are thought to be predicated on information that is in our spectrum. But we also want a way to verify that this model result is an accurate representation of the data. So the next step that we employ is computing model spectra. And we do this using the MolSim code, which is software written by members of the collaboration for reproducing molecular spectra. And basically what this does is it just takes in the spectroscopic info of whatever molecule you're looking at and the best fit parameters of the MCMC to compute a spectrum that can be directly compared with your data. And now I'm switching to the molecules that we're actually studying for this work. So this is CH3C4H, both the A state, which is shown here in a k equals 0 line, as well as the E state, which is shown with a k equals 1 line. And we see that this MCMC routine did a very good job of reproducing at least this line, but if we look at other lines in the spectrum, it would look very similar. And usually this is enough. We say, hey, this is an accurate representation of what this molecule is doing in TMC1, and then we can do our analysis. But in some cases, you might run the MCMC on a molecule and you get lines that look like this. So this is CH3C7N, which these are individual lines which, based on the results of the model, they fall below the noise level of our survey. But there's still information that our routine is picking out to produce these lines. And we want to cover all our bases and kind of make sure that there is actually information that's contributing to this. So in this case, we need to add another step. And that step involves the spectral line stacking of these molecules. So you take all the lines that appear in the GOTHAM survey and you co-add them on top of each other at 0 rest velocity. And this is done to sort of boost the signal to noise and also bring out features that might not have been present because they were under the noise level for individual lines. So now I'm switching back to CH3C4H, which as we recall was very bright in its individual lines. But when we stack this, we stack both the data, which is shown in blue under the red curve, and we also stack the model, the Molsim model, that was a result of the MCMC fit. And that is shown in red over here. And we see that both, just like in the individual line, the stacked emission of CH3C4H is very well reproduced by the stacked model of CH3C4H. And to assign a number to how well this is reproduced by our model, we do a matched filter analysis, which is essentially just convolving this red line with the blue line and finding the position at which it best fits the data, which ideally, if you have a good detection, is going to be at 0 rest velocity. So this is what this process looks like for a fairly bright molecule. Let's see how it looks for some of those very, very weak molecules that do not show individual emission lines in our data. So let's actually take it back to the very first step for these molecules. So the first step was we run the MCMC, which fits all the data where there are transitions of both CH3C7N and CH3C8H. And these are the cumulative distribution functions, which you can think of these as sort of the probability that whatever parameter you're looking at is less than a given value. So you expect after a certain amount, it should get to 100% if you have a good fit, and you want it to be a steep curve if it's a really good fit, because that's when you know exactly what this parameter is. And then we also see the covariances of all the parameters as well. And I should note that this is just a subsection of the MCMC results, because this has both the A and E column densities in log space for both of these molecules, but I'm not showing things like rest velocity and line width because it would be too hard to see what's going on. But at first glance, these results of our fit, they look pretty similar, but if we look closer, particularly at the numbers on these axes, we can actually see that the left corner plot is a much better fit than the right corner plot. And that we can kind of see in that all of these covariances, as well as their cumulative distribution functions, are constrained to within well under an order of magnitude for CH3C7N. Whereas for CH3C8H, we see some of these much larger kind of blobs, and some of them actually span many orders of magnitude, which means this is not a very, very reliable fit, and the model is not able to find very significant information on this molecule in it. But nevertheless, these are, by default, these parameters are consistent with our data in some way. And the only question that remains is whether the information that contributes to that is from emission, or rather a lack thereof. And so we again use Molsim to simulate the best fit results of these, and then we stack the spectra and perform a matched filter, and the results we get are shown here. So on the left, we have CH3C7N, and we see that there is a statistically significant amount of stacked emission that is actually really well produced by the Bayesian model, which is shown in red. And once you perform the matched filter between the two, you get a peak impulse response of about 4.6 sigma, which is significant evidence that this molecule is actually present in our data, and that we've fit its column density and other parameters with this routine. On the other hand, CH3C8H, as was kind of indicated by the very broad sort of fit that was very uncertain, we do not see any sign of stacked emission in this one, and there's no response from the matched filter. So on the left, we have evidence for a new interstellar methylcyanopolyene, and this would be the largest symmetric top ever discovered in space. And so because of that, we're going to adopt the parameters fit by the MCMC in our analysis of all these chains. Whereas for CH3C8H, we can't be confident in the column density that the MCMC derives, but we can be confident in the upper limit that it sets. So we're going to use that to do our analysis. So this was very exciting to see, and it's going to be really cool to compare this with what we see for the other members of these families. So for all these are the results for all the carbon chains for the stack and the match filter. And this is just to illustrate how well the model does at fitting some of the other molecules that we create here, other than the new ones. And we see that it does a fairly good job, and that we can take these parameters in our analysis. So now let's look at those parameters. Let's get down to exactly what these molecules look like in TMC1. So here's a table of some of the more important ones that we fit, including column density, as well as excitation temperature. And these are both split up into both the A and E symmetry states because we've treated those completely separately. And the first thing I'll note is that the excitation temperatures for the methyl polyenes is systematically larger than the excitation temperatures for the methyl cyanopolyenes, with the one exception of the E state for CH3C3N. And this is actually behavior that has been identified in previous literature on these molecules, where these do always have a higher excitation temperature, but we're not entirely sure why. So that was very interesting and good to reproduce. But when we look at the column densities and compare it with some of the other families that exist in TMC1, we can see some really, really interesting trends that are great to look at. So here I'm plotting the total column density. So this is adding both the A and E states together. And we're plotting that as a function of how many carbons are in that carbon chain. And we're plotting it against the cyanopolyenes, so these are the linear species, as well as the carbon chain radicals. So these have the form C and H, and they're shown in green. And of course, the methyl cyanopolyenes are shown in red, and the methyl polyenes are shown in blue for how we observe them. And we can pick out some really interesting trends here. So we see that all of these species exponentially decrease with the amount of carbons in the chain, which is expected and good to see. But we also see that CH3C7N, which is newly detected here, very well follows the linear trend in log space, of course, that is set by the previous two ones. So it's really cool to see that this chemistry is so continuous in that sense. And furthermore, the trend line for these methyl cyanopolyenes is very similar in slope to the normal linear cyanopolyenes, which is shown in pink here. Whereas on the other hand, the methyl polyenes in blue match the carbon chain radicals very well. So this is direct evidence that the chemistry between the blue species and the green species is related, and that the chemistry between the red species and the pink species is related as well. And it's really impressive how well, I mean, in the case of the carbon chain radicals and the methylpolyenes, how closely it does that. And then lastly, for looking again at the methylpolyenes, if we look at the upper limit that we place on CH3C8H, we actually see that it kind of forces, it kind of breaks the linearity of this. Whereas if this molecule was following the same trend that was set by these two molecules, we would actually have expected to detect some amount of emission from it in our spectra. But the upper limit we place shows that it's a little bit discontinuous and it drops off to some extent. And this is actually something that, that is seen for the carbon chain radicals as well. So that's actually cool to reproduce as well. And then if we also look at the ratios of the A&E symmetry species, which of course we treated separately in our analysis, we can see some really interesting bimodalities here. So what I'm plotting here is the black line here shows the A to E column density ratio that you would expect if the molecules were in a thermal or Boltzmann distribution at a given temperature. And the dots here are what our data suggest for what these ratios actually are. And it can be thought of that anything below this black line is in a superthermal A to E ratio distribution, meaning it's not equilibrated to the excitation temperature in TMC1, or if it's above this curve, it's in a subthermal excitation ratio between the A and E symmetry states. And we see a very stark difference between the two families that we've considered here. With the methylpolyenes, they all exist in a superthermal distribution relative to what we'd expect from a Boltzmann distribution. Whereas with the methylcyanopolyenes, the shorter species are below this curve. They are superthermal, but when you get to the longer species, they actually cool past the thermal distribution. And this is a really, really interesting behavior. And it's very stark between the two, that they're so different. And this is really pointing to separate formation conditions or processing mechanisms that's driving this. And we can't know for sure exactly what is causing this, but here are a few possibilities. So first, one of the main ways that you form these molecules is through the dissociative recombination of these larger hydrocarbon species that are ions. And it's expected that these reactions are very highly exothermic, and because they release so much energy, they can produce equal amounts of both the A and E symmetry states, even when you're at the very cold temperatures in TMC1. So that could be what's going on to force these dots to be below the black curve here. Whereas if you have, say, a neutral-neutral reaction, that is not necessarily going to produce the same amount of A and E populations. So it could be closer to the Boltzmann curve or above it. But it's not quite well known how many, or what the relative amounts of A and E that is produced through these. So we can't say for sure that this is going on. Another thing that could be happening is a result of something that was studied in 1993 by Willis et al., is that the conversion from the A-E symmetry state to the A symmetry state could be occurring on dust grains. So either your molecule formed on a dust grain and desorbed off it, and it would then have an A to E ratio similar to or subthermal to the temperature in TMC1, or you formed the molecule in a gas phase and it was stuck to a grain, it absorbed on and then subsequently desorbed off. That's one way that you can convert from E to A. So it could be, these also could be indicative that the methylpolyenes do not form preferentially on dust grains, whereas the methylcyanopolyenes may either form preferentially on them or they may stick to dust grains more often. So these are just a few ideas, but there really needs to be more laboratory efforts to study really how these A and E symmetry species are produced in conditions like in TMC1 to really explain what is going on here. But it's really interesting nonetheless. Lastly, we compared the results of our analysis with a chemical model. This was run on the Nautilus code, which uses the Kita reaction network, which has been expanded to include CH3C8H, as well as some other molecules that have been studied in the GOTHAM survey. And this model has been used successfully for some of the linear species like the cyanopolyenes. And here are some of the parameters of the chemical model and the results. So this is a plot that is very similar to the one I showed a couple slides ago. So it's plotting column density or abundance as a function of how many carbons are in the chain. But now the solid lines here are the results of this chemical model, whereas the dashed lines are the results of our data, of what we actually observed in TMC1. And the first thing I'll note here is that the methyl chains are consistently underproduced by the model. The only exception to this is CH3C3N, which has a few extra formation routes that are accounted for. And this could be why we're seeing an overabundance here. But other than that, all the species are underproduced by the model, indicating that there may be some more formation routes that we're not considering here. And then furthermore, if we again look at the slope of these chains, how their abundance is decreased with the amount of carbons in them, we actually reproduce that slope very, very well with this chemical network, particularly in the methyl polyenes in blue. We see it's very, very similar, as well as some of the layer species for the methyl cyanopolyenes. And furthermore, we also reproduce the fact that these slopes are common between the blue and the green line, as well as the pink and the red line, where you have a steeper slope for the methyl polyenes and the carbon chain radicals than you have for the methyl cyanopolyenes and the cyanopolyenes. And if we look at the different reactions that are going into this network after the fact, we conclude that for both of the families, these dissociative recombination reactions really are the dominant formation routes for the methyl chains. So in this case, you would have a more saturated positive ion, like it's shown here. You need a nitrogen, obviously, to form the methyl cyanopolyenes. And we conclude that these are really the things that drive the chemistry of these methyl chains in TMC1. But this does not explain the A to E symmetry ratio populations that I showed on the last slide. Because if it really is equal, and these are both being produced by these exothermic reactions, you would expect their A to E populations to be about the same. Well, that's really, really interesting, and we still don't really know why that is, but we do know that these are important formation routes. So to summarize, we did this robust and consistent analysis of of 6 different methyl carbon chains in TMC1. And with our Bayesian MCMC routine, we found statistically significant emission from methyl cyanotriacetylene, CH3C7N. And then we subsequently compared all the column densities and relative A to E symmetry states for all these species and found some really interesting results. And we see that their chemistry is similar in that they're both mainly produced through these dissociative recombination reactions, but there's also some intriguing differences pointing to their different chemistry, notably the fact that the methyl polyenes fall off at a certain column density, as is indicated by our upper limit on CH3C8H, but also that the A to E ratios are all superthermal for the methyl polyenes, whereas they have a larger spread for the methyl cyanopolyenes, and we can't quite explain that yet. And with that, I'd just like to thank you all for listening, and I'm happy to take any questions now.
All right, fantastic talk. Thank you very much, Mark. So it looks like we do have a few questions already lined up. The first one comes in from the chat from Glenn Langston. He asks, the table in the previous slide, so that was before the A and E ratio, I believe. showed lower excitation temperatures. Why are these plotted values higher?
So right here.
Yeah, those are the ones I was talking about.
Okay, so you're talking about the ADE ratio or the excitation temperature?
The excitation temperatures. I just, the plots I thought you showed were like above 10 Kelvin, and all these numbers are below 10 Kelvin. Is there just a factor that I'm missing?
Could you remind me what plots you were talking about? I don't know if
The
I showed
next
any
plot.
plots with excitation temperature.
So go to the, so you showed this plot, then you go to your next slide.
Yes.
And that one there.
Oh, yes. So this is showing the kinetic, this is the kinetic temperature, not the rotational temperature. We would expect, this is as measured by a study that looked at ammonia in TMC1, and we'd like to compare it with the kinetic temperature, since if it's some sort of collisional driving process that's putting these ADE ratios where they are, that would be reflected here. And that is not necessarily going to be the same as the rotational temperature, which is what is shown in the plot here.
Mhm.
So I guess kinetic temperature is what that should have said on the next slide.
We have a lot of HC9N data, and that was showing us like about a 4.9 Kelvin excitation temperature in our fits too. But that's why I was more consistent with these numbers.
Right.
I'll mention that you, I'm sorry, go ahead.
Mark, I had Glenn, finish your comment, then I'll ask my question. It's related to this excitation stuff.
Yeah, the only comment is also that because as you get to have a larger and larger number of carbons, you actually, there's a dilution effect that we mentioned in our paper on HC7N, that there's actually there's more and more power in the isotopomers of these things. So it's for HC7N, it was like about 5% of the molecules are actually in the isotopomers. So they wouldn't be at the frequencies you list. They'd be at, whatever the isotopomer frequencies are. You could probably detect those maybe for the
Shorter ones.
Yeah, the shorter ones where you have a lot more power. So maybe you could see that. So you might be able to do the isotopic numbers also.
Yeah, that would be a great follow-up work, is to see how the isotope logs differ from any of this. If they have the same ADE ratios, would be really interesting too.
Yeah, I probably wouldn't get to that, but you might be able to just get the abundance.
All right, let's go with Herschel's question.
Hey, Mark, nice talk, nice results. I was wondering how polar are the methyl cyanopolyions relative to the methyl polyions? Could that explain some of your subthermal excitation? I imagine the cyanopolyions would be much more polar. So do you know what the dipole moments are in this series?
I don't know the dipole moments off the top of my head.
Right. That polarity.
So what kind of process are you suggesting? So that could drive this, you mean?
Yeah, I mean, you're seeing that the cyanopolyions are subthermally excited, right?
Yes.
And the polyions are less subthermally excited.
Correct.
Right?
They're actually super thermally excited.
Are they? What's the thermal? What's the temperature that you're using?
I guess compared to the kinetic temperature, they are
right.
Excited.
Right. I mean, when you say thermal, I mean, relative to what? So I assume you're talking kinetic temperature, right?
Right.
So look, I think you need to look at the dipole moment of these series to ensure that you're covering the basic excitation.
Right.
I mean, and that might feed into what you infer from the chemical modeling as well. So I was just wondering what the dipole moments were. For example, in the fact that you see CH3C7N but not CH3C8H, I think that's related to the greater polarity of the
Yes,
of the
that is
chain.
definitely, that is
Right.
very true. And that, like, so if we look at there is a bit of like detection bias here, because those methyl cyanopolyenes have those larger dipole moments. They're showing up much brighter in our data. So that's why
Right.
we get 100 sigma from CH3C3N, but only 83 from this one. So even though the methylpolyenes are more abundant, they're actually dimmer in our data because of those dipole moments.
Right. And so I strongly suspect that some of your excitation questions will, looking at the there's rotational excitation of polar molecules, right? By there's a paper by Harvey List, excitation by electrons and as well as the microwave background, right? So the larger the polarity, I would think that the greater the subthermal excitation, degree of subthermal excitation.
Right.
If you notice your excitation temperatures, they're close to, if you go back to your table, they're close to 3 Kelvin for the A species.
Mm-hmm.
And both A and E in the cyanopolyenes.
Yes. Yeah.
Slightly larger. Okay.
Yeah. Just
so I suspect that it has to do with the polarity of these chains, these effects that your relative polarity.
Right.
So you look
So
into that.
I think that would do a great job of explaining the excitation temperatures. I'm not sure if it could, I need to look more into it. I'm not sure if it could explain the A to E ratios, because you can't interconvert between the two ratios.
Sure. But look at, consider them separate molecules, so A series, E series, and then see what the contributions are, otherwise, really nice results. Thank you.
All right, we have still just one more minute before the hour. So is there anyone else who'd like to ask a quick question of Mark? Okay, if not, I thought I'd just ask one quick question of you. So with your merging of all the individual potential spectral lines in order to get a stronger signal, you are looking just at the overall emission rather than individual spectral lines.
Right.
And so you are, not necessarily seeing some of them, but you can still get a lot of information out of the individual lines and their relative strengths. Have you attempted, or are you able to do any sort of backtracking based on the total emission in order to predict the values of some of those lines that are hidden among the noise?
Yeah, so that's it. That's essentially what I was showing with the individual lines that were below the noise level. That is what the MCMC does predict, and that's kind of the power of this algorithm, is that it can pick out statistically what excitation tempered is describing that, even though those lines are below the noise level, because you have the cumulative information of all those different things. It's very hard. It's a very complex routine, but it's really, really powerful.
Okay. All right. Well, it's 1 o'clock now. So I think with that, wish to give you one final thank you for joining us today.
Yeah, thanks for having me.
Fantastic talk. And for those that are still on, we will not have a lunch talk next week, but we will be back the week after. So thank you very much, everybody.